Hello everyone, I'm Dr. Vandana Masi, Assistant Professor of Physics in KIET Group of Institutions, Ghaziabad. In today's lecture, we'll study about diffraction at end slit. The contents of today's lecture are theory of diffraction at end slit, intensity distribution due to end slits, missing order at end slits, formation of spectra with grating, dispersive power of a grating, and these will be followed with a few numericals. What do you understand by diffraction grating, simply grating, or the end slit arrangement that we are about to study? So, an arrangement made up of a large number of parallel slits of equal width separated by equal opaque spaces is known as a grating. Gratings are made by drawing equidistant parallel lines on a transparent material with a fine diamond tip. The lines drawn are opaque to light, while the spaces between them are transparent to light, and these spaces act as slits. So now we consider a section of the plane transmission grating, which is AB. A monochromatic light of wavelength lambda is incident on this plane transmission grating. Now by Huygens principle, we all know that each slit sends secondary wavelets in all directions from wavefront W, W'. Each slit will act as a single slit, and therefore we have an N single slit arrangement. Let us consider that the width of each slit is small e and the width of each opaque space is small d. Then E plus d, this is known as grating element. The secondary waves traveling at an angle theta with the direction of incident light or with the horizontal will reach point P1 on the screen. And we have to find out the intensity of point P1. Now the intensity at point P1 is found by using the theory of diffraction at single slit that we have seen in a previous lecture. The wavelets proceeding from a slit is equivalent to a single wave of amplitude A sine alpha upon alpha, and these waves are considered to be starting from the middle point of the slit. Alpha is equal to pi upon lambda e sine theta. The path difference between any two consecutive waves is E plus d sine theta, and phase difference between two consecutive waves therefore becomes delta, which is equal to 2 pi upon lambda into path difference. So here it becomes 2 pi upon lambda E plus d sine theta. We write this as 2 beta. Now we have studied the resultant of n simple harmonic motions, and using the same thing we find out the resultant intensity at point P1. For us, now A, small a, it becomes capital A sine alpha upon alpha, small n becomes capital N. Capital N is the number of slits in the grating. Delta is equal to 2 beta. And now if we substitute all these in the equation for resultant of n simple harmonic motions, that is R equals to A sine n delta by 2 upon sine delta by 2, we get the resultant amplitude at P1, and that is R is equal to capital A sine alpha upon alpha sine n beta upon beta. Intensity we find out by squaring this amplitude, and intensity therefore becomes I is equal to R square, which is equal to capital A sine alpha upon alpha square sine n beta upon sine beta square. It is important to understand that the first term, that is A sine alpha upon alpha square, is due to diffraction from single slit, while the second term, which is sine n beta upon sine beta whole square, this is due to interference from all the slits, that is n slits. Intensity distribution due to n slits. We shall now analyze the different intensity conditions. The first case, that is the case for principal maxima. Equation 1, which we just saw, will take a maximum value if sine beta is equal to 0. Sine beta equals to 0 implies that beta is equal to n pi, where n can take values from 0, 1, 2, 3, so on and so forth. Or if you substitute the value of beta, we get pi upon lambda e plus d sine theta is equal to plus minus n pi. Or solving further, we get e plus d sine theta is equal to plus minus n lambda. Here, n equals to 0, n equals to 1, n equals to 2, and so on. They correspond to 0 order, first order, second order, principal maxima, respectively. The plus minus sign shows that there are two principal maxima of the same order on both the sides of 0 order maxima. We shall now find out the intensity of principal maxima. In order to find out the intensity of principal maxima, we use the L'Hospital rule. This rule is used only because if I put the condition of principal maxima from equation 2a in equation 1, we get an indeterminate form, which is the 0,0 form. So now we use L'Hospital rule. In this rule, we will differentiate the numerator and denominator separately till the time we get an acceptable form after applying the limit. So now we get limit beta tends to plus minus n pi sine n beta upon sine beta. We differentiate sine n beta, the numerator, separately with respect to beta, and we differentiate the denominator sine beta separately with respect to beta. After differentiating, we get n cos n beta upon cos beta, and now we put the limit, that is beta tends to plus minus n pi. Now if you put this limit, you get n. So the intensity of principal maxima becomes A sine alpha upon alpha square capital N square, and this is equation number 3 for us. Next, we find out the condition of minima. Equation 1 will take minimum value only if sine n beta is equal to 0. Please make sure that sine beta is not 0 for minima, because that is the condition of principal maxima. Now sine n beta equals to 0 gives n beta equals to plus minus m pi, or capital N pi upon lambda e plus d sine theta is equal to plus minus m pi. Please remember, I have substituted the value of beta over here. So after solving, we get n e plus d sine theta is equal to plus minus m lambda. It is important to note here that m can have all values except 0, capital N, 2n, 3n, basically multiples of capital N. Because for these values, sine beta will become 0 and we will get the condition of principal maxima. So for us, m takes all integral values like 1, 2, 3, so on till n minus 1. Then we don't take n, and the next value is n plus 1. And from here, we take all the other integral values, but stop when it is 2n. And further, we continue when it becomes 2n minus 1. Therefore, there are n minus 1 minima between two successive principal maxima. Next, we find out the condition of secondary maxima. There are n minus 2 secondary maxima between two principal maxima. And in order to find out their position, we differentiate equation 1 with respect to beta and equate it equal to 0. So we equate it to 0. So we get di by d beta is equal to capital A sine alpha upon alpha square to sine n beta upon sine beta capital N cos n beta sine beta minus sine n beta cos beta upon sine square beta, and this we have put equal to 0. Now we all know that here a sine alpha upon alpha cannot be 0, sine n beta upon sine beta cannot be 0. So the remaining term, that is n cos n beta sine beta minus sine n beta cos beta is 0. If we solve this, we get capital N tan beta is equal to tan n beta. Now this can be written as tan n beta is equal to capital N upon cot beta. If we draw a right angle triangle wherein we have kept the sides to be n and cot beta, so our hypotenuse becomes under the root n square plus cot square beta. So using this right angle triangle, we apply Pythagoras theorem and we get sine n beta is equal to capital N upon under the root n square plus cot square beta. And this is the condition that holds for secondary maxima. Now using this value of sine n beta, we try and find out the value of sine n beta upon sine beta square. And that gives us capital N square upon n square plus cot square beta sine square beta, which is equal to n square upon n square sine square beta plus 1 minus sine square beta. And solving it, we get n square upon 1 plus n square minus 1 sine square beta. We substitute this value of sine n beta upon sine beta square in equation number 1 to get the intensity of secondary maxima, which we denote by capital IS. So IS becomes A sine alpha upon alpha square within brackets n square upon 1 plus n square minus 1 sine square beta and whole square of this. So from equation number 3 and this equation which we just found out, we get the ratio of intensity of secondary maxima to the intensity of principal maxima is 1 upon 1 plus n square minus 1 sine square beta. If n is a large number, then the intensity of secondary maxima will be negligible. And in reality, in the gratings that we use, n is extremely large. It is a very big number. So secondary maxima are not visible in grating spectrum. So now, if you see here the intensity distribution graph due to n slit or grating, we see that we get a zero order principal maxima right in the center, and we get the first order principal maxima on both the sides of it, again second order principal maxima on both the sides of the zero order principal maxima, and in between these principal maxima we have n minus 1 minimum conditions or positions, and we also have n minus 2 secondary maxima positions, but since these secondary maxima aren't visible, so they have not been plotted. Now we come to another very important topic, which is missing order at n slits. We just found out the condition of principal maxima due to n slit. Now sometimes for some values of E and D, the interference maxima due to n slits and diffraction minima due to single slit, they are formed at the very same position. So the combined effect results in certain missing orders of interference maxima. The direction of maxima due to n slits is given by E plus D sine theta equals to plus minus n lambda, where n is equal to 0, 1, 2, 3, so on and so forth. This is the equation that we just found out. Similarly, direction of diffraction minima is equal to E sine theta equals to plus minus m lambda, where m takes values from 1, 2, 3, so on and so forth. And this equation we saw when we studied diffraction at single slit. For missing orders, both these equations are satisfied simultaneously. So we divide them and we get E plus D upon E is equal to N upon M. To make this further easier to understand, let us take a few examples. Let E equals to 3D. If we put these values, then we get N upon M is equal to 4. If I take the values of M as 1, 2, 3, I get N equals to 4, 8, 12. So this simply implies that interference orders 4, 8, 12 are missing in the diffraction pattern. Let us take another example. Let us consider 2E is equal to 3B. On solving this, we get N upon M is equal to 5. For M equals to 1, I get N equals to 5. For M equals to 2, I get N equals to 10, and so on, so forth. So this simply implies that interference orders 5, 10, 15, 20, so on, they are missing in the diffraction pattern. Now we study formation of spectra with grating. We have studied the equation of principal maxima due to a grating, and that equation is called the grating equation. So for us, the grating equation is E plus D sine theta is equal to n lambda. You have to understand that E plus D, which is the grating element, is a constant quantity once you have fixed the grating with which you are working. So now, for a given wavelength lambda, angle of diffraction theta is different for principal maxima of different orders. For white light, for a particular order of n, different wavelengths are diffracted in different directions. Longer the wavelength, the angle of diffraction will be greater. We know that red light, red color, has the longest wavelength, so red will be diffracted the most, and violet color has the least wavelength, the shortest wavelength, so it will be diffracted the least. In the direction of incidence, that is n equals to 0 and theta equals to 0, we get maxima of all wavelengths. So here, all wavelengths coincide to form the white central image. Principal maxima of all wavelengths corresponding to n equals to 1 form the first order spectrum, and those corresponding to n equals to 2 form the second order spectrum, and so on. So here in the figure you can see that we get a central image which will be white in color for white light. Then we get the first order spectrum on both the sides of the central image, and here violet will be diffracted the least, so it will be closest to the central image. Red light will be diffracted the most due to its wavelength, so it will be farthest from the central image. This was for the first order spectrum. Similarly, you will get the second order spectrum, third order spectrum, so on and so forth. Dispersive power of a grating. It is defined as the rate of change of angle of diffraction with change in the wavelength of light used. If angle of diffraction changes by d theta, then wavelength changes by d lambda. Dispersive power is expressed as d theta by d lambda. For a plane diffraction grating, the grating equation that we just saw is E plus d sine theta equals to n lambda. Differentiating this with respect to lambda, we get E plus d cos theta d theta upon d lambda is equal to 1. Solving this, we get dispersive power d theta by d lambda is equal to n upon E plus d cos theta. You can solve this further for different forms, and you will get many different forms of dispersive power. To understand things better, we see a numerical now. We are given a grating has 7,000 slits per centimeter. When a monochromatic light is incident on it, a second order bright line is formed at 30 degrees. Find the wavelength of light used. In order to solve it, we see the things that are given to us. Grating element E plus D is equal to 1 upon number of slits per centimeter, which happens to be 7,000 in our case. Solving this, we get 1.4 into 10 to the power minus 6 meters. The order of the principal maxima given here is n equals to 2 and theta is equal to 30 degrees. So principal maxima due to grating is given by E plus d sine theta, which is equal to n lambda. Here n can take values 0, 1, 2, 3, so on and so forth. But in the given question, it is given that n equals to 2. So we substitute the value of n equals to 2 and we get E plus d sine theta is equal to 2 lambda. Substituting all the given values, we get lambda is equal to 3,500 angstrom. So this was all for diffraction at n slit. I hope you understood. I shall see you again in the next lecture. Thank you.